First of all, thank you, Bob, for the opportunity to present. I think this is the third year we've presented progress on the FlexSpec-1, Freudian slip. Thank you to the FlexSpec team for setting me up for this. Sorry, for setting this up for me. And thirdly, you will have gathered by now that I am not Jerry Foote, okay? Oh, thank you. My name is Tony Rodda. I represent the British contingent of the FlexSpec team. I do have a funny accent. We do have English speakers in here for later. If you find some difficulty with anything I say, just put your hand up and pull me back. Okay, I've got a thick skin. In fact, Siri and Alexa both think I am Dutch, Australian, and whatever. So just bear with me. So what am I? You know who I am and who I am not. What am I doing here? Well, we have produced a spectrograph over the space of about 3 years. And what I want to show you is some of the lessons we learned from that project. And I think it's important to establish the start and the beginning of the project before we go into the detail. This started about 3.5 years ago at a symposium just like this one in Flagstaff. And a group of us were sitting around a beer, complaining bitterly about how spectrographs work and all the known issues. And if you are a spectroscopist, you will know what we're talking about, because spectrographs are just a big bundle of compromises, and you have to learn to manage them. And we quickly moved on to what we would like to see in a spectrograph, a wish list, okay? And we felt as though we had some kind of initial design criteria or document, and the main protagonist of the team, Woody Sims, said, well, why don't we just do this? Why don't we build it? And what we did was, I wouldn't pay too much attention to this wish list, because by the third beer, we had reinvented the Hubble. So don't pay too much attention to the original, but here, this is distilled from that original requirement. And the requirement was quite simple. We wanted to do more science. And we thought we could build a good spectrograph with a good range of resolution that amateur spectroscopists could take with reasonable DIY skills and build themselves, and thereby get around the issue of having to buy different spectrographs to do different science. And we could address the known issues and help them deal with those. And we wanted to have some fun learning too. Round about that time, a real Dutchman by the name of Paul Gerlach had produced a wholly 3D printed machine. And Woody said, well, you've been printing these things and similar spectrographs for a year or two. Why don't we start there? And that was the starting point, okay? A 3D printed spectrograph. Fast forward 3 years. 6 months ago, I commissioned the first FlexSpec-1, our spectrograph. That is, I think that's Clark Yeager's machine. We're starting to bring these online more and more. It's taking data. I'm going to show you a brief review of the data. That is the machine. Those are the CAD files produced by Jerry Foote, the real Jerry Foote. And this is without the case. And I'm going to walk you through these individual components in a moment and show you the lessons we learned from that. Does it work? Oh, yes. When you see spectra and your spectra look like everybody else's spectra, that's incredibly reassuring, okay? For non-spectroscopists, it's the right shape, all the emission features are in the right place, it's well calibrated. Now I need to back that up, don't I? This is a spectrum taken with an early FlexSpec. Oh, yeah, come on. The blue plot is from my machine. You can tell it's an earthbound machine because there's the tellurics at the top end. The red plot is from the Miles database. So this is a Miles standard star. It's just a test. The important points to note are calibration is in excellent agreement. The shape is really well matched. This was the reference curve was produced by using a different Miles star. So the overlay is real. Okay. How good is that? This was produced in ISIS. And everybody knows, everybody who's done spectroscopy knows ISIS. And I used it just for the credibility factor. This is from the calibration data. And these are the residuals and the RMS value from the FlexSpec-1 calibration. And that figure there, 0.04, is not just in the ballpark. As Americans would say, that's on the pitcher's mound. That is absolutely on the ball. And that compares really well with commercial spectrographs. Now, I've committed a cardinal sin here in that I've overlaid lots of plots, but this is just to give you some confidence that the detail is in the spectra as well. I think I can point out there's the magnesium triplet, there's the sodium doublet up there. The green plot has a really nice H beta absorption feature here, which is turning into an emission. That was purely serendipitous. That was just, I managed to catch that. But there's some gorgeous detail in there too. Now we're producing something like R equals 1700, 1800 at the first pass. Theoretically, it should be 2300. But we'll not get ahead of ourselves and quote our figures from the deep red. Let's keep it real. Or 1700 or 1800. So you've seen the starting point. You've seen the end point. The machine we're using follows closely Paul Gerlach's classical layout. Now, if you're not if you're a spectroscopist, you know this, but if you're not, I'll just outline this. The light from the telescope comes in from the top end, hits, excuse me, hits a reflective slit. D is a folding mirror. Its job is just to make the spectrograph a bit more compact. It doesn't really do anything from a spectral point of view. E is the collimating lens. It produces a collimated beam to the grating, F. The dispersion comes off the grating to the objective, the camera lens, G, and across into the science camera, which isn't shown. Up at the top end, the guide unit is a transfer mirror, a transfer lens, and the guide camera, which would sit here. So there's nothing spectacularly new about the actual design. It's well known, it's well trusted, okay? But we did learn an awful lot about this when we worked through it. And that's where we're going to start. First of all, let's deal with the elephant in the room, because when I said, let's produce a science quality spectrograph using 3D printed materials, I could physically see the shoulders sag. the big issue is in the UK, which is a wet rock in the North Atlantic, I can get really good results from a low spec, from a printed machine. That's because I don't have any much thermal changes to manage. Across here in Arizona, New Mexico, California, you've got something called the sun. Yeah, right, we'll leave that one there. And the big issue is that PETG with carbon, which is a really good printing material, has something like 3 times, 2.5 to 3 times the thermal expansion rate of aluminum, there in America. And even that is twice what a steel comparison would be. We did all sorts. We put styrofoam cases around the machine. We put heated beds underneath it. We tried all sorts. Clark Yeager tortured this thing. He put it in his ice box. He put it on the with temperature sensors, and we watched the flexure happen. And we just said, look, we can't live with this. So let's take that one on the chin and let's put in a steel base. So when you saw that card earlier, let's go, there you go. This is all 3D printed materials, something like 40 odd components, but the base is steel. Okay, so let's take that one on the chin, push it to one side, and get on with it. Okay, top of the list in that gripe session was focusing. Every spectroscopist has had a problem with focusing. Some of us nightly, and it comes from 2 areas. Firstly, there's thermal expansion that causes loss of focus. And when I'm talking about focus, I'm talking about focus on the slit, not telescope focus. And also, we are projecting a curved image onto a flat surface, which is why you get fishtails. So even that, even focusing is a compromise, even if you get it right. So we thought we'd address that. So what did we do? Really easy. Instead of paying $150 for a good quality achromatic doublet, let's just spend $50 on a really good commercial camera lens, which is designed to give you a flat field. Okay. And yes, there's a couple of more surfaces in there, but you know what? We can live with that. We can live with a couple of percentages loss. It doesn't matter. It gives you a flat field. And that gets rid of the vast majority of that fishtail. Secondly, let's not focus the science camera. Let's not change the focus rather. Because if you talk to a spectroscopist and you say, you're out of focus, what did you do? 9 times out of 10, they'll come back and they'll say, well, I adjusted the science camera. No. The science camera, if you talk to Clark Yeager and Jerry Foote, they'll tell you, don't touch the science camera. It should be focused on infinity and left. So what does that mean? Well, it means that you've got to focus something else, and the only thing you could focus else is the collimating lens. So right up front, we said, let's lock the science camera onto the science camera lens, focus on infinity, set and forget, lock it in place. You can buy a dog, feed the dog, train the dog to bite you if you touch the camera. But you don't touch the camera, okay? That means that you've got to focus the collimating lens. If you focus the collimating lens is in the middle of the spectrograph. How do you get to it? So right up front, we said, we'll automate it. We will automate the focusing of the spectrograph, okay? This is a design Jerry came up with. The real Jerry. The collimating lens sits on a sled. There is a coarse focusing when you set the actual spectrograph up. This stepper motor operates an eccentric cam, which simply moves the collimating sled back and forwards, only by a millimeter or so, but that's all you need. And this thing, you can rotate this, just let it rotate. And you can watch the calibrating lines from the calibration spectra broaden and focus and broaden and focus. It's delightfully simple and it works a treat. And I think, being British, I like irony. And I like the idea that we are using 3D printed components to compensate for the expansion of steel. You know, give it up. So this is it, and it's delightfully simple, and it's modular. You can take this and use it in your own spectrograph, just, you know, whatever. So that's what we did. The second issue was stray light. This petrified us. It really did. When I show you what we came up with, whatever happens in commercial spectrographs, I shudder to think. Now, the stray light comes in two different forms. When I was setting my spectrograph up, I focused the camera lens. I put a mirror in place of the grating so that I could focus the collimating lens on the slit. This is a highly magnified view of the slit, probably focused. And you can see there, it doesn't look very focused, does it? That's because this is a photograph of the Fraunhofer diffraction coming through the slit. And I'll show you what that does in a moment. Give it a Wayne Green, and Wayne Green does the Wayne thing, and he does some analysis, and he comes up with this plot which shows you the main lobe. This is what we want to use in the spectrograph, and these lobes here are part of that diffraction pattern. And this shows in background counts on the chip. It shows as noise. We did lots of experiments. I mean, Wayne drove us crazy talking about stray light, and we replicated Young's experiments and all that kind of thing. We went into this in some detail. And quite clearly, the answer was to baffle stuff. Baffle the heck out of this thing. And then Clark came along and he said, I think you should look at this because this is a problem. And our shoulders sagged when we saw this. What you want to do is you want to pick the first order coming off the diffraction grating. Clark had assembled his FlexSpec without first painting and flocking the inside of the machine. He put a collimating instrument, just a small laser on the front of the machine, on the telescope port, and up and trace this thing, trace the light path through. Now, I'd seen some of this. I'd seen some ghost images, but I didn't know where they were coming from. So what Clark pointed out was, yes, if you put the first order down the throat of the science camera, the second order goes straight back out the collimating lens. In fact, if you got it just right, you could clip the edge of the lens and you could light it up like a neon. The +1 order hit the back of the slit holder and straight into the camera lens. So we had loads of noise that until you actually stretch the contrasts and look at things in detail, you don't know is there. And this is there in every commercial spectrograph. This is an expanded view of what's happening up here. That is all noise. So the answer was to baffle everything. Okay, this is an exploded view, an end-on view of a baffle that goes on the back of the slit, and it takes out those extra Fraunhofer lobes. These pointy out bits are baffles. Clark came along and said, let's put baffles in, let's build light traps, stop those orders going everywhere. And Jerry said, well, instead of putting them in the base of the spectrograph, let's fix them to the lid of the spectrograph. Set the spectrograph up, drop it in, job done. You would not believe the improvement in contrast. Unbelievable. All the ghost images changed. You know, as spectroscopists, we tend to focus on this band across the middle of our chip image, and we ignore everything else. There's so much data in there about how your spectrograph's performing. And that's what we did. Then there's a grating. Don't touch the grating. Well, you've got to touch the grating. If you want to select the wavelength, and usually the way it's done is with a vernier, and you adjust the vernier gauge and it pushes on an actuator arm, a lever, and that turns the grating. And they both have different expansion coefficients. So whatever you're going to do, there's going to be movement in that grating, even for commercial spectrographs. So we looked at this and we said, is the bearing really smooth? Can we improve this? Jerry's design. Automated the wavelength selection. Up. Down here is a bearing. Underneath is two pairs of neodyne magnets. I think I've got a picture of this somewhere. There you go. So this is the grating holder turned upside down. That's where the bearing fits. Two pairs of neodyne magnets acting on a washer underneath the bearing. It grips the washer and it provides drag. We do the actual wavelength selection. We always approach it from the same direction. So you take up the slack in the gears. It is repeatable. You can slew this thing a couple of thousand angstroms if you want, and it will go back to the same place within a couple of pixels. Job done. There's the grating holder. That's the detail. We built in a small hole sensor to provide a homing mechanism. So if you get lost, you could press the home and it will go back to a reset position. Wavelength calibration, we could do 3 hours on this. What do you do when you calibrate? You dangle a bulb over the end. That's an attempt to use the telescope optics to replicate what you're seeing. It's never going to work. It's near field. Your telescope is focused on infinity. It's always, you read page 74 of Tripstein and Walker's book. Clark came back and he said, if you move that calibration source, your calibration lines move. So let's build it into the spectrograph. Now, this sounds like a cheesy marketing strapline. That's because Greg and I are both marketing and we wrote it. The Kazin ring is a complete solution. What do I mean by that? We tried to produce, we used lenses, we used integrating spheres, anything we could think of to inject the calibration bulb data into this spectrograph. Nothing worked. And then we came up with the Kazin ring. The Kazin is a mythical creature, don't worry about it. It's just, we couldn't think of anything else to call this thing. On-axis calibration, this fits inside a 2-inch nose piece on the front of the unit. A picture paints 1,000 words. This is the actual Greg Jones designed this. On here are posts for the calibration for the Relco lamps or for the neon lamps, whatever you want to use. These are LEDs. LEDs UV boost grain of wheat to produce a lovely flat. So this does calibrations, flats. There's also a couple of markers in there, red, green, and blue, so that if you slew the grating and you don't know where you are, you can switch the marker on and find out where you should be. It's delightfully simple. There it is. There's a cutaway. Greg's got this. He can demonstrate this to you. There's the board. The board faces outwards and illuminates a ring, an annulus, which matches the focal ratio of your telescope. And you view the target through the ring. It's there all the time, which means that you can turn the calibration on and view the target at the same time. There it is. This is the body. It sits inside the nose piece, and these LEDs and lamps illuminate the screen, the ring, and that's how we inject. And it's a Lambertian distribution, and we flood the slit, and it works beautifully. You know, when I quoted that RMS figure before, I was talking to Jim Grubb about this. Beautifully flat field. I got a linear fit to the calibration, which was 0.07. A linear fit. Just quickly, my scope is stored horizontal. I took calibration data, slewed it to the other side of the sky through meridian flip, calibration target, calibration target, calibration target, calibration target, brought it back to the, it was on the same centroid. The first calibration and the end calibration was on the same centroid. I did it again and did what you're not supposed to do, and I slewed the grating 1,000 angstroms into the blue and brought it back, and on a 4,500 pixel dispersion axis, it had moved by 3 pixels. Now, I'm not excusing the 3 pixels. I know where that is. It's in the bearing. But it is so stable as to be scary. We can do flat fields with it. We can augment the flat fields with other LEDs to give great counts down in the blue. It's all there, okay? And you need to see Greg's little demonstration later. The guider, how come that we get 95% of the light, 99% of the light fed off to the guider, and we produce such poor guide images with poor fields of view? Well, all we did, we used 2 lenses as the transfer. It's just a variation on a theme, but we did it in a way that is flexible. That is the M3. The field that I get on my 1500 focal length machine telescope is about 25 by 18. And that plate solves. That tells you everything you need to know. And what we did, this is again Jerry's design. One lens sits in the bottom, which is it's separately focusable. One lens sits at the top. That's where the guide camera goes. You put the guide camera in, focus on infinity, and then you screw this in on a helical focuser until you see the slit. And it's as easy as that. And it gives you those results that I just showed you. The key thing is that you can change these and shorten this to fit your particular focal length. So it's flexible. That's all we've done with that. I've used the word automation quite a bit. We've automated the collimating lens, we've automated the grating, we've automated the calibration. The word automation keeps popping up. We wanted to use this remotely. There's Clark's machine. This is a board about 3 inches by 4 inches, designed by Greg Jones. This is an Arduino Nano 33, IoT or BLE, doesn't matter. room for 4 stepper motors, a whole range of sensor capability, a couple of DC bucks for power. This is a 230-volt generator for the calibration lights, lamps, and this whole thing sits on the top of the spectrograph, fully hands-free. The code, Wayne's going to talk about the actual code and how we do this later. Where it's controlled, this is where my presentation ends. And that's why we've just got this on the left-hand side. Wayne is going to populate the right-hand side. This is a web page. The web page talks to a little Raspberry Pi server on the top of the machine, 1 Ethernet cable in, 1 power cable in, that's it. So in summary, we think we've achieved our objective. It is fully automated. It is science data grade. It is science grade data. It's a DIY project that anybody can undertake. It's all round about R equals 2000. I've just put a 900 grading in and it's showing 3000 plus. It's highly modular. You don't have to build the thing. You can take bits of it and use it somewhere else if you want. And I did bulk slightly at putting that on the bottom, but it is free. In true Paul Gerlach style, we were giving all of this back to the community, all the design, all the engineering drawings, all the software, how to get the boards, where to order them, the whole full bill of materials, yours. Thank you for being a very attentive audience and for putting up with the accent. It's been my pleasure.
Questions?
Thank you. Yeah, where do we order one? Thank you very much. I, of course, had a very different approach yesterday that I described with the spectrometers I've built, which were simple machine shop. The other big distinction was that I worked by myself. I'm not either bragging or complaining. The sophistication that you all have brought in that team effort, would drive me nuts when we're doing it. But on the other hand, you see the quality of the results. The work I did is nowhere near the quality of what you've done. I do have one, it works and so forth, but you really do see the results of a constructive team effort carried out over whatever it is, 3 or 4 or 5 years. And I really congratulate you for that.
Thank you.
I do have one technical question, which is, one of the things that drove me in my design and approach was the f3.5 and from the telescope. And I could not see how to do a design like yours at f3.5. So I'm curious about what your F range is that you can plausibly do. For example, you rather quickly said, oh, we use a camera lens. Well, I obviously tried that too. The trouble is that my design, again, it has pros and cons. My design really could not accommodate whatever you said, a $50 or $75 camera lens. I tried it, and within the range, yes, it greatly improved the spectrum, but it didn't have the acceptance angle I could use.
Yeah.
So I'm curious, what is your F number? And you know, if it's a 3.5, I'll throw mine away.
Ideally, this is round about F6, F7, F8.
Yeah, okay.
But we have got one member of the team has an F4.
Okay.
And he's keen to try this.
Okay.
Of course, there's going to be vignetting. You're going to lose some light. Doesn't matter what you say, you are. But because all the card files are parametric, you could, in theory, enlarge, put bigger lens in here without much to do, really. So I don't know, I'm not going to make any promises. 3.5 is a bit of a stretch.
Yeah, it's a That's what I thought.
Yeah.
But you do with what you got.
Everything is a
Yeah,
compromise.
I think that's the real lesson that you and those of us who've tried to build a spectrograph,
Yeah.
everything is compromise after compromise. And the compromises between the compromises.
And the ripple effect is unbelievable.
Yeah, that's
But
right.
thank you for the comments, because I'm the mouth up here doing this presentation, but I am truly standing on the shoulders of people.
Oh, you all have obviously done a terrific job.
Thank you.
Thank you.
Yeah, but I mean, mine's f6.5. It works great. F7, F8. I've gone to F10. Good throughput. Enlarges the spot size, but we use an OVO disk with different slot sizes. So again, it's flexible. You can adjust that for the different spot size.
Hey, Tony, as being new to SAS myself, can everyone in the room on your team stand up?
Absolutely.
This is an amazing result. I mean, what an engineering achievement.
Spot on. Yeah, can you, come on guys, stand up, don't be shy. Greg Jones, the electronics expert. There's Jerry, the design guy. There's Woody, who kept us on the straight and narrow. Clark, who tortured things. The analytical stuff that came out of Clark's brain was amazing. Yeah.
Do we, John Martin, do we have the people from home available? Is Frank Parks on the watching us this morning?
Sorry, I didn't catch that.
Is Frank Parks watching us this morning?
I do
He's
know.
one of our team members who, if you look through the screen, he's probably standing proudly at home.
What Frank did with the CAD files, he I don't know what package he uses, but he can fly through the spectrograph following the light path. Remarkable stuff that he came up with. So yes, Frank's not here. And Tom Smith, should mention Tom Smith. Some of his code was remarkable.
This is Clark, and I brought my spectrograph. So if anybody wants to see it, they're more than welcome to take a look at it. I'm going to give a little demonstration of some of the functionality at the end of the day. So anybody that's interested is more than welcome to stick around and
Fabulous.
take a look.
It weighs about what, 2 kilograms. So it's not onerous.
Maybe this is part of the talks that come after, but what's next? I know you're not finished.
Okay, the FS2 is next. Because this is modular, and that was part of the design. That's the design ethos. It's modular, we can reuse stuff. So we're going to look at fiber injection and all that kind of stuff. Haven't decided it yet. No promises. We're still discussing it. That's what's next.
So I'm Greg Jones, one of the team members. At lunch today for the spectroscopy group, I think we would love to hear ideas about what people want for FS2. The design thought right now, this is great for, say, 12 inches and below, but we've got a lot of team members that are pushing 20 to 30 inch scopes.
Mm-hmm.
And so the probability is something for a larger scope, but we would love to hear what you think you need.
That's a great point, because this came together, like I said, half a dozen of us over a beer. So I like the prospect of 50 people having a beer.
Our commercial spectrograph manufacturers aware of what you did and going to incorporate any of these features?
So I didn't quite catch that.
So our commercial spectrograph manufacturers, are they aware of this and going to incorporate some of what you did?
They are now. Look, commercial spectrographs are also built to a price point. And we all know what the issues are. We all know the compromises. We all know they leak light. We all know they've got problems, but but that's the way we've traveled very far in a very short space of time. And that includes the commercial guys. I'm absolutely sure that they must do. I mean, the reflections and all that kind of thing, they must do. That's their issue.
All right. Thank you so much, Tony.
Can we have one more?
We have one more.
Good point about the commercial manufacturers. But am I correct in guessing that a lot of these additional features that you just talked about, we can probably retrofit them into our commercial instrument?
Well, I would like to have a go at that. Yeah, why not?
You know, I'm thinking like the baffle behind the slit. That sounds like a no-brainer.
It does. It does. But especially Greg's Kazin ring.
Yeah.
If that fits into a 2-inch nose piece, you can put that anywhere. And actually, the big board that you saw, you don't need the big board. Greg's got a little board run with the Shao, which is the size of your thumbnail, which will run the Kazin ring. Just think about that. You can put that anywhere.
Tony, this is Jerry. I might also add that all of this information, design, software, board design is open source. We have a GitHub and it's all up there.
Yep.
And we've got some design tools. For example, the business of the guide lenses, how to size those for your focal length and your guide camera chip size. There's a spreadsheet up there that will help you figure out the optimum way to do that to maximize your field of view on the guide.
Just to ask, being someone, and I'm sure there's other folks in the audience today who are somewhat lacking in time, is there any way that members of the team or some outsourced group would be willing to manufacture a few of these and sell them to us?
Okay, I'm surprised that one didn't come up earlier. When Stan Watson saw this working, his first question was, what are you going to call the company and how can I help? No, we're not manufacturing. We're going to produce 1 or 2 units to repay some debts. But apart from that, it's not really what we were set up to do. It's fairly straightforward to do, a modicum of DIY skills, you know, it's not onerous.
Okay, thank you, Tony.
My pleasure.